Jeff Hester, why did you decide to look at the Eagle Nebula with Hubble, and what did you find?
Well, we looked at the Eagle Nebula because we were interested in seeing what happens when massive stars form. Massive stars are very hot, they're very bright, and they produce huge amounts of intense ultraviolet radiation. And as that happens, it boils away the cloud that they're forming from. And so if we could have the first image, this is a ground-based image of the Eagle Nebula. And what you're seeing here, the stars up in the upper right-hand corner are these young massive stars. And everything else that you see is kind of a bowl-shaped cavity that these stars have hollowed out in the cloud that they formed from. We were interested in studying this process to see what happens right at the edge of that cloud as material is boiled away. And so we selected those objects that you see right in the center of the frame there to go and study with the Hubble Space Telescope. So if we could zoom in on those, what you see now is a ground-based image, and we're now going to see the Hubble Space Telescope image of those features. This is what you see. And I'm going to look at it for a second. The first time we saw those data, we were just blown away, running up and down the halls at Arizona State, showing them to everybody who was around. It's kind of spectacular to look at a picture like that and realize it's not an artist's conception and something on the cover of a science fiction book, but it's real, it's out there. If you look at this structure, you can see along the surface kind of rays pointing out, and that's the material that's being boiled off of the surface of these dense columns of interstellar gas.
Those are those white rays at the top of the black column.
Those are the kind of white rays poking out, almost like porcupine quills poking out from the surface of that. But beyond that, we also saw some fairly spectacular things. If we could have the next frame zooming in on the top column of that, here's a blow-up. And you can, again, see all of the material just streaming away from the surface. But another thing that you'll notice there is that there are a bunch of little globules of gas all over the place in there. You see these tiny little features. Each of those is about the size of a solar system. We have named those things evaporating gaseous globules, which also lets us refer to them as eggs, a nice handle. But the other thing that we realized is that embedded within those eggs are being uncovered as the material around them is boiled off. Embedded within those eggs are forming stars. And that in fact this process of evaporating the cloud is actually limiting the masses of the stars that are forming inside of that cloud.
Okay, and of course that picture was about a light year high, the Hubble picture.
The whole thing from tip to base is about a light year in that.
So what we're seeing is perhaps a new way that stars form, or a way that limits the mass that a star can form. So it's a way to make a star not get any bigger as it's sucking in material from the surrounding cloud. And that's what's really new here. And we'll talk about that a little bit more later. Yeah. But since we start out with the nebula, and we haven't talked about nebulae too much in a while on Space Astronomy Update, when we get Dr. Ann Kinney to tell us about a nebula. What is a nebula and why are we interested in them?
Well, this nebula lives in our Milky Way, in our home galaxy, and it's one of a type of object that has a lot of active star formation in them. We astronomers refer to these as very dense, very cold, and very massive objects. Now, when we say dense, they're dense in terms of the kind of medium you see between stars in the galaxy. If we were to compare it instead to densities on Earth, it's much thinner than the best vacuum that we can make on Earth.
A thick nebula is really a thin vacuum.
Yes, exactly. Now, how can you form stars out of something so thin as a vacuum on Earth? Well, the way you do it is that these complexes are vast. They're very large. The size of the largest pillar in the image that Jeff just showed you is 1 light year long. That's a light year of material. So you have cold and dense, in astronomical terms, material that is very vast and therefore can form stars. Now, these clouds are very dark until the first stars turn on, and then they're very light. So they're both the darkest and the lightest things that we see in our galaxy.
Okay, and so if we can form stars from a nebulae, tell us a little bit more about the stars you see forming in the Eagle Nebula.
Okay. There are sort of two pieces to the story. The first piece is is almost more like archaeology than astronomy. There were these star-forming cores buried down inside this molecular cloud, and along came the intense radiation from these massive stars, and it, sort of like a windstorm in the desert, blows the light sand away and uncovers rocks and things that are buried there. This radiation from the stars boiled away the cloud and uncovered these little globules. And so the first part of the story is archaeology. But the second part of the story, which is now looking at a fundamental physical process going on in the universe, is that, well, the way that stars form is that you get enough mass together that gravity is able to cause that mass to start collapsing. And as it gets smaller and smaller, you form an object in the center called a protostar, and more material falls on it. If left to its own devices, if just left in isolation, what will happen is material will keep falling on the star more and more until finally the star starts to become a real star. Things start to happen in its interior. You're on the verge of nuclear burning happening in its interior. And when that happens, the star turns on a wind. And that wind blows away, and it disperses the material that it was forming.
But it's already a pretty big star.
But it's already a pretty big star at that point. And the important thing is that in that case, the star decides for itself how big it wants to be. Here, though, what we seem to be seeing is that process is interrupted. That these stars are down in the molecular cloud. They're forming, materials falling on them. This process is going along until along comes this intense radiation from these nearby massive stars and disrupts the whole thing. It disperses the cloud that these stars were forming from. And so it freezes that process. The stars now don't get to decide for themselves how big they're going to be, but instead they're frozen out at kind of random places in their evolution.
Okay, and Bruce Margon, there has been a lot of controversy, and mainly just a lot of questions about what is the right theory of star formation, how do stars form, and what do you see as the contribution to that from this, or is it making it more complicated?
Well, Jeff is right. Perhaps the biggest prize in understanding star formation is to understand why does a star pick the mass that it ends up with. Nature actually has terrible quality control in making stars. There's a huge variation of masses that they end up with. They range from anywhere from about 10% of the mass of our sun up to several hundred times the mass of our sun. And however it picks that number, it's then stuck with that for its entire evolution of many billion to 10 billion years, and it determines all future properties of the star. The total luminosity of the star, the way the star chooses to die, whether it dies a quiet birth, a quiet death, or some kind of violent death like a supernova, all of those factors are determined by the mass. There's been a huge controversy about what is the underlying thing that makes a star decide to choose. And the controversy has run along the lines, as in many evolutionary controversies, of heredity versus environment. The heredity would be, you just got what you got. A cloud started to contract. If it started out weighing 2 times the mass of our sun, you got a 2 solar mass star. If it started out weighing 1/10 the mass of our sun, you got a 1/10 solar mass star. But the evidence here, at least in M16, is now overwhelmingly strong that it's environment. It's not heredity. These stars are starting to contract, but they're doing so while being blasted by the powerful radiation field, the powerful light of other stars that is shaping them, shaping these structures with very sharp edges.
Which are kind of the big brothers that formed first from the same cloud.
And so a later forming star is, in some sense, being told, you will not get any bigger than this amount because it's forming in this blasted environment, sort of like erosion. If I could have our slide, our geological slide, we see evidence of this kind of process around us on Earth all the time. It's not particularly exotic. That is, the process of erosion on Earth does determine what structures look like.
Okay, you've got the Chiricahua mountaintops.
Right. These are the Chiricahua Mountains in southeastern Arizona. And you see dense rock that presumably started as a much more uniform, homogeneous structure, and an eroding medium, in this case, of course, water and wind, chewed away at the lighter, frothier stuff and just left the dense columns. In the case of star formation in M16, lighter gas is blasted away. The eroding medium in this case, of course, is not a liquid. It's powerful light from the previous generations
And you
of
get
stars.
these three big black
And
columns.
we get these, not only do we get these huge elephant trunk type columns, but we also get these tiny wispy tendrils coming off of the columns. It's clear that all of the structure in this image is being, or much of the structure in this image, is being determined by the sandblasting field of radiation. So at least in this case, and probably by analogy in many other cases of star formation, it's environment, not heredity, that is making these stars decide how big to grow.
Well, Jeff, maybe you can tell us a little bit about those tendrils and what you think is going on
in
here.
fact, while we're talking, if we can cue up the cartoon, we've got a set of drawings that kind of show this process. What you see here is the little black ball that you see in the center there is representing one of these globules. And it's really what it is, it's the innermost, densest part of the gas that's falling toward this forming protostar. And it's buried down inside the molecular cloud. But coming in from the upper right-hand corner, the wavy lines there represent the intense ultraviolet radiation that's falling on the surface of the cloud and is boiling this material away. So the little arrows that point away from the cloud there represent material streaming away. That's material that we see in these images. But what happens is that the globule itself is denser, and so it resists that process longer than its surroundings. So if we could have the next frame, as you go along, the surroundings are dissipated, but the globule remains. And in fact, the globule, its shadow, kind of protects the material behind it a little bit, so that if we could have the next image, you see that they get further and further out. Here we've got a drawing of a globule that's now almost completely isolated from its cloud. And then finally, the last cartoon shows a case where, in this case, the globule is now completely broken away from this cloud. But I also want to call your attention to the little glint that they're showing on the front of that. That little glint is the artist's way of indicating that there's something else inside that globule, and that's the star that's forming in its interior. And what happens is the globule actually gets boiled away from one side until the star itself is uncovered. And so if we could go to the image with the arrows, I'm going to show you a couple of real examples of that.
And this is now the picture from the Wide Field and Planetary Camera 2.
This is now the Hubble Space Telescope Wide Field Planetary Camera 2 picture. And the two objects that you see there indicated with arrows, the one on the lower right you can see especially well, there's a little bright thing sitting there. That is a star that was inside of one of these eggs, and it's just been uncovered. And you can in fact see the remains of the egg and the remains of the little stalk, the shadow of that egg immediately below it. And so even though we don't get to watch a single one of these objects go from being buried down inside the cloud to being uncovered and finally the star emerging, what we do get to do, since we see about 50 of these things in the nebula, is we can see some of them that are just starting to be uncovered, some of them that are uncovered a little bit further, some of them that are uncovered a lot further, and finally some objects like these two where you've actually boiled off enough of the egg itself that you finally get to see the star that's lying at its center.
Okay, well, Bruce Margon, we saw earlier in Jeff's opener the ground-based photo from the 60-inch telescope at Palomar Observatory. That was pretty nice looking to the uninformed eye, including mine. What is it about the Hubble observation that made a difference in developing this information?
You're right, Steve. It's important to recall that these elephant trunks, the huge structures, are of course visible from the ground with a normal telescope. Hubble's extremely fine angular resolution, however, gives us all sorts of details here that really crack open the picture for the first time. First of all, they show us that the edges of the trunks are incredibly sharp, very, very thin. This transition from sort of trunk to no trunk occurs in sizes that are the size of an individual solar system. And those angular sizes are far too fine to ever be able to image from the ground. This is the main reason that we're so confident that there's this erosion process, that this evaporation by radiation is going on, because you see this finely blasted edge that is very, very sharp. Now, the little eggs and the tendrils that attach them to the elephant trunks are simply too small in angular size to be able to resolve from the ground at all. So the general picture that there were these big fuzzy trunks there was available from ground-based images. But the interesting interpretation that it's due to this erosion requires having the very fine resolution of Hubble and the very, very sharp edges.
Okay, well, I know both Ann and Jeff have things to add. Start with Ann. I hope someone's going to mention brown dwarfs before we...
Well, that's what I wanted to ask about. You're discussing, both of you, about how you can cut off the mass of a star this way by basically evaporating the material that would generally fall on and form a more massive star. Does that help us create brown dwarfs, which have been difficult to understand?
Yeah, that's an interesting question. The first kind of star formation that I talked about, normally when you look at stars forming in isolation, there's enough mass around to make something actually much bigger than the star that you actually wind up making. There's plenty of material, and the star decides for itself when it's going to turn on and blow this wind and shut down further infall. But in that case, you've got plenty of mass, and you're probably going to make a real star, because it's not going to stop forming until you formed a real star. But in the case of M16, since
the Eagle Nebula.
Pardon me, the Eagle Nebula. In the case of the Eagle Nebula, we're freezing that process at totally arbitrary places. And so if today, inside of one of those eggs, inside of one of those little globules, there's an object that only weighs 5/100ths of a solar mass or 1/100th of a solar mass, an object too small to go on and become a real star, that's as big as that object is ever going to get, because you've shut off any further infall of material.
I think
onto it.
this is a really important point, because until maybe June, it depends on what reports you credit, brown dwarfs, and I'll remind our listeners in a minute what they are, were purely hypothetical. But since June, there have been at least 3 pretty credible reports that brown dwarfs have been found. And these were the long hypothetical objects that are intermediate in mass between a true star and a planet, but which are believed to form like a star does, and they would normally be expected to have less than 80 times the mass of Jupiter. And there isn't a real agreement on this as to the lower limit, but one definition I've seen recently in a paper by theorists was that they'll count anything more than 10 times the mass of Jupiter and less than 80 as a brown dwarf. And the difference between a brown dwarf and a star, other than the brown dwarf is a lightweight, is the brown dwarf doesn't have enough mass to generate enough pressure at its center to make it hot enough and dense enough to turn on the stable nuclear reactions of burning hydrogen and shine brightly like a star. So they're hot a little bit when they form, then they cool away. And it was a problem for the leading theory of star formation that we couldn't that it could not explain how to make brown dwarfs. And we said, fine, no one's found any. Now they're starting to find them. It's good that now we know a way to make them.
Now listen, as long as we're talking about hypothesis, can I just go way into hypothesis and say, could you guess then that there are some stars that are going to form with a nice little disk around them and thus have planets, and other stars that are unfortunately close to a really hot star and will have their disk blown off them and will not form planets around them?
That's fun stuff to speculate about. In fact, in answer to that question, I'm going to back up a little bit and say that this work on M16 is kind of an example of the way that good science happens sometimes. We had specific scientific goals that we were after. Namely, we were after studying how material boils off the surface of these clouds. And when we got there, we found data that told us all about that. We see that happening, and what we learned was wonderful. But also, courtesy of Hubble's phenomenal resolution, we discovered these new objects. And so here we are talking not about the science that led us to take the images, but in fact talking about the science that discovery led to, and speculating about brown dwarfs and planetary systems. To now answer your question, if I were going to speculate,
please.
And I promise it's nothing but speculation. If you look at the way that disks form around stars, very early in the process of forming a star, you probably don't have to make much of a disk, because the material in close can probably fall directly down onto the star itself. It's later in the game, as material is falling in from further out, that it can't fall directly onto the star. It has to instead fall onto a disk, and the disk has to carry it in. If we've caught some of these objects early enough in that process, and I stress if we have caught some of these objects early enough in that process, then maybe these are objects that aren't good places to look for planets, because maybe we've caught them before they've had a chance to form disks, and before they've had a chance to gather the material around them that might become solar systems.
So at least in that direction, we may be alone.
Well, at least in this particular object, that any time that you talk about this business of star formation and all of these questions that we're talking about, it always gets around to this kind of a question. Because in the end, not only are we studying star formation in our own galaxy, but really what we're studying is what must have happened in our own neighborhood 4.6 billion years ago, when the sun and our solar system was formed.
But it's going to happen there in the Eagle Nebula, so that's kind of back to the future.
That's right. We don't have the option of
Right.
going back 4.5 billion years ago and watching our own system formed.
And we don't have the option of going on too much
okay.
longer. So,
Let me make a comment about these timescales, actually. The very fine boundary that Hubble images lets us actually calculate the rate at which this boiling away is going. And most of the timescales you hear about in astronomy are ridiculously long, and our sun is 5 billion years old. So we can actually calculate that if we came back and imaged the Eagle Nebula only about 10,000 years from now, it would look very different. This is a very, very rapid stage of evolution. And so, amusingly, even though one tends to think about cosmic things as going very, very slowly, this nebula is actually eroding away faster than some of the terrestrial erosion analogs. It's a beautiful example of something that's changing in the cosmos very, very
it's
quickly.
a terrific picture of a dynamic universe. I think we do have to sum up and say that I do want to mention that there's a detailed scientific analysis by Dr. Hesser that's behind all of this. We're not just talking from a pretty picture. There's a scientific paper that's been submitted to the Astronomical Journal. But I think we've seen at least one of the ways in which stars form. We've seen a process that's not really been considered before that may explain how the smallest stars and the objects even smaller than stars, how they can arrest their development and be created with those low masses. And I know the panel wants to add some stuff.
I want to add one more thing. And the
Okay.
reason I want to add one more thing is that I was told whatever else I do to get this next visual on there because it's so neat.
You're right.
So I'd like to run the tilt now, and I'd like to kind of finish what I have to say with a little bit, little philosophy behind this. We've talked about a lot of the detailed science that we're seeing. If we can run the tilt, we've talked about the detailed science, but at the same time, we're showing a picture that is just a spectacular image, a picture of a thing that's really out there in the universe. And it's a little bit like the first photographers that ventured into the western United States and sent back pictures of Yosemite and pictures of Yellowstone and pictures of the Grand Canyon. Apart from understanding the details of the geology, it was just an awe-inspiring thing to people to realize that those were real things that are part of our nation. And in this case, I like to point to this image and say that all of the detailed science aside, this is a real thing that's part of our universe. And it's fun to be a part of that activity.
I think we'll see this picture again. Don Savage, back to you.
Thank you very much. Thanks, panelists. And at this point, we're going to take questions from the reporters here and at NASA Centers. We'll start here at headquarters. And if there's any questions here, please wait for the mic and give your name and affiliation. We'll start down here with Paul. Please, Mike will be here momentarily. Thanks.
Thank you. Paul Hoverston, USA Today. A couple of questions for Dr. Hester. You sort of got into a little bit about the possibility that our sun might have undergone this sort of process. Could you speculate on that? And also, secondly, these gases that get evaporated off, do we know anything about their composition, what kind of gas we're talking about?
Okay, I'll start with the second question. If you were following the speculation that we were just following, if I were to speculate, I'd say that maybe this is not the environment that our sun formed in. That maybe what we're going to find as we continue this investigation is that to form things like our solar system, you have to have stars that are more in isolation, and so get to see the process through to completion themselves.
Because the area where the planets formed might have been blown away.
Because that might have been blown away. And again, I emphasize again that speculation, but it's certainly the kind of question that we're now going to try to follow up on. The other question that you were asking, what are these columns and what's really happening here? These columns are actually dense clouds of molecular gas. It's mostly molecular hydrogen, composed of 2 atoms of hydrogen. Mixed in with that is a fair bit of dust, which is why you can't see through them. That's why they're dark. The dust blocks the light coming through. And what we found, again, the reason we studied these in the first place was to study how the material boils off the surface of these. And one thing that we didn't mention that I'll mention now is that that part of the science was completely successful as well. It turned out that the profiles that we take across that agree perfectly with the calculations that people make of what that should be like.
But let me just point out one more thing about this. As you go from the interface of the elephant trunk to the ionized region next to it, you're going from a dense, cold region to a very thin, very hot region. And again, to connect it to our experience on Earth, we don't get that kind of range in temperature here on Earth. We live in a much more benign environment with very little temperature change and with very little change in going from thick to thin. There's a huge difference in how thick that column is in the elephant trunk and how thin the surrounding ionizing material is.
Okay, next question, Dave.
David McAlery, Voice of America. If I understand you right, some of the older siblings are the stars that are blowing away the stillborn stars.
Right.
All right. Now, are some of these globules that don't form fully into stars, are you saying that they may become or may be brown dwarfs?
Okay, first of all, a number of the globules that you see, what's inside them will go on to become fully formed stars. Infrared images of this field say that a number of these have objects in them that appear to be 3 or 4 or 5 solar mass objects. And so some of these have full-up stars inside them. But what we are saying is that it's possible that embedded inside of some of these are objects that have not yet become stars, and those are possible brown dwarfs. In fact, a very interesting thing to do is going to be to follow up getting spectra of a couple of those objects that have just been uncovered and to look at them and see if maybe those are brown dwarfs. Who knows?
Or you could just come back 10,000 years from now when they've uncovered.
That's right. Or you could just come back.
That's going to be your proposal, right, for HST?
But in all fairness, the reason it's so fascinating is that in our solar system, we'll never know. 4 billion years has gone by while our sun has been blasting away all traces of this birth material. So there is no chance of ever recovering whatever similarities and differences there were in the evolution of a middle-aged star like our sun, because this birth environment has been totally swept away. And that's why it's so fascinating to watch it happen in detail here.
Harry?
I'm Harry Rosenthal, the Associated Press. That leads me to my question. One, I gather that this nebula is not unique, that there are others out there like it that you could look at. Are there some that you might have as a target that are farther along in their development, where some of these stars may have been much farther exposed?
Well, that's a very, very good point. We already mentioned when we were talking about the Eagle itself that the way that we know what happens as these globules are uncovered is that we find some of them that are just being uncovered, some of them that are further uncovered, and some of them that the stars are popping out of, and we piece those together into a story. And it's the same thing in the bigger picture as well. You can look at interstellar space with radio telescopes and with the IRAS satellite, and you can see huge clouds of cold molecular material. And then inside some of these huge clouds, you find cores that you think might go on to become stars. In other places, you find regions that these clouds have formed a few stars, but there aren't very many yet.
Core is a dense localized clump.
A core is a dense localized clump. These little globules you might think of as cores. In other cases, then you come to M16, places where a few especially massive bright stars have turned on and have just changed the total character of what's going on around them. You can find other regions like M16 that are further along in that process, and you can also find regions that are so much further along in that process that now stars have started to explode in supernovae, and leading to things called supernova remnants. And so it should emphasize that this is not just one little piece, and that, if you'll pardon the pun, that the science that we're talking about today exists in a vacuum. But instead, we're looking at one piece of a much larger puzzle, a puzzle that people have worked on from the ground with all of the different satellites that NASA has flown.
Now, you can...
And it's an especially pretty piece of that puzzle, perhaps, but it's one piece of that puzzle that goes together into a big, coherent picture of how it is that stars manage to come to be.
That's really my question, though. Are you going to, assuming that this is a fairly young in the evolution, are you then going to go to another nebula where they're halfway through and in other words, get the whole range of ages?
Maybe the right response to that is that the proposals are in the mail. We have some other objects that we have looked at that we're not talking about, but that I'll say we've got some neat stuff that we've seen already. And we've also got a program to extend this kind of investigation to other objects as well.
I was going to address the other end. He's talking about nebula that are more advanced, but you can imagine if you had one where the really bright and massive star had not yet broken out of the nebula, you wouldn't see the thing yet. But those things emit in the infrared, and with the next generation of telescopes, with the telescope or the instrument called NICMOS that will be put in the refurbishment mission, you'll start to be able to observe things that are even in a younger and earlier state than the Eagle Nebula.
And that's
so you can go in both directions of age.
That's going to be added to Hubble in February '97.
Could I have one brief question? Could you talk about the pictures that were left on the cutting room floor? How many other pictures did you have?
Actually, I think that this gentleman right back here, if I said too much, he'd come after me. No, you've seen a number of them. We've released images of Herbig-Haro objects and talked about that process of star formation. We've released some images of supernova remnants and talked about late in the stage. Today, we're talking about the Eagle. But this is an ongoing enterprise, and I certainly expect that we're going to find some other fascinating things.
We release them all when they're ready for scientific publication.
Right. We're very careful not to glance at them for 5 minutes and imagine we know what they mean and then run out and start showing them.
Kathy?
Kathy Sawyer, The Washington Post. Just to further clarify, I take it you're saying this is a new part of a normal star-forming process rather than a twist on an aberrant process in an atypical location?
I guess the question is what you call typical. A question that I can answer today is exactly what fraction of stars wind up going through this process as opposed to the other process. This is the kind of thing that people have speculated about a lot. What happens? People have speculated for a long time that when stars turn on, especially when massive stars turn on, that they would have an effect on star formation going on around them. But exactly what that effect is hasn't been clear. In some cases, it might trigger new star formation. What we have here is a very clear look at a case where it's shutting down ongoing star formation. I wouldn't call it aberrant because we see a lot of regions like this. And if I had to guess, when we go out, now that we're sensitized to look for this, when we go and look in some more likely places, my guess is that we're going to find a number of regions that have objects like these in them. And so it's, rather than saying it's an aberrant form of star formation, maybe it's more correct to say that there are a number of different ways that star formation can occur, and that we're getting an especially nice look at one of those.
It's like most heredity versus environment arguments. Ultimately, both people are right.
That's right.
So here's an example where we're finally positive that the environment plays a strong role. But it's and so we know it happens, at least here, but it's probably not going to turn out to be a clean black and white issue, that it's always A or it's always B.
Right.
It's probably going to turn out to be often a mixture.
Absolutely, yeah.
Follow up, would this remarkable image look the same if we could see it with our naked eyes in terms of color and?
It's as close to true color as we could produce from the data that we had. What you're actually looking at there are 3 different pictures that are put together. And the red picture is showing you red light coming from very, very cool, cool or isn't it? Low ionization is the right word, but fairly dense low ionization gas. The blue picture is coming from much more tenuous, higher ionization gas, which is actually a line, an emission line in the blue part of the spectrum. The only place that we really fudged is that the green picture in that image is actually looking at a line that's more red than
Part
green.
of the spectrum.
Part of the spectrum. So it's not exactly what you would see if you just saw it with your naked eye, but it's pretty suggestive of the range of colors that are there.
But you won't ever see it with your naked eye unless you move
like
to
that.
Sagittarius.
Not like that you won't.
And housing's very expensive there. So.
Right.
Move to take questions from the Marshall Center now in Huntsville, Alabama. Please give us your name and affiliation, and go ahead.
Hi, this is Martin Berkey with the Huntsville Times. Could you give me some idea of the age and size and perhaps a little of the origin of the entire Eagle Nebula?
Okay, sure. The overall size, the nebula is, maybe 10 or 20 light years in size, depending on how far out you want to go and say that's part of the nebula. Studies of the stars in the nebula suggest that the oldest stars there are only 1 million or so years old, and so this is actually a very young region of star formation that we're looking at here. So if you could go back 1 million years ago and look at this, you wouldn't see anything like this. You'd in fact just see a large molecular cloud with a few isolated centers of star formation in it. But all of the structure that you see there has occurred over the last couple of million years as the intense light from these first very massive stars that form was able to eat into that surrounding cloud. Does that answer your question?
Yeah, that would. For instance, any one of those little tubes, I don't know if you can call up any of the pictures or do a pointer or anything. How long does it take it to uncover some of those little finger-like projections?
Okay. It seems, based on indirect evidence, we think that it takes probably about 10,000 years to uncover one of those. And the way that we know that is that we can calculate the rate at which material is evaporated from the face of that cloud. And so we can calculate how fast that it's eating away into the cloud. And then if you look at this picture that's on the screen now, we can say, well, the furthest of these objects are such and such distance away from the surface of the cloud. And if you just say, there's a distance and I know the speed, you can calculate a time. And that time turns out to be about 10,000 years.
I know this is far out, but is there any possibility that things like Jupiter are out there? Is it possible that Jupiter may be one of those little globules that sometimes in its past?
Well, that's a little bit what we were talking about when we were talking about the brown dwarf issue. The idea that possibly this is a way that you can form star-like objects that aren't big enough to be stars.
I'm glad that Martin asked that, because it occurred to me as we were coming down here in the elevator that this is, if you can make brown dwarfs like this, you can make free-floating Jupiters. That is, you make things perhaps that are indistinguishable from a planet, but they didn't form the way a planet is supposed to form in a thick accretion disk around a star. And there are theorists with way out ideas about explanations for the dark matter in the halo of our galaxy who always talk about free-floating Jupiters, and nobody could say whether that made any sense or not. I don't know if we can say that now, but we could imagine that if someone found one, we might have an instant theory to explain where it came from.
Well, I'd be very careful in going too far with that speculation, because to bring it back to what we're really studying today, we're studying a specific process going on in a specific place. But again, as we talked about a little during the earlier conversation, that what you're really seeing here with this speculation is what scientists do, that they see a process like this, and one of the exciting things about these results is that they immediately lead us to start thinking about all of the what-ifs and all of the could-bes and looking for other connections between phenomena. And it's following up exactly those kinds of connections that is going to lead to some of the science that comes from this, because it's going to be those ideas that we now take and try to test in looking at this object and at other objects in different ways.
continue on from Marshall. Go ahead.
First of all, it wasn't clear whether you thought that our solar system, our sun, and perhaps Jupiter formed out of just such a process as this. And also, if you might, if you can point out on the picture some other areas that aren't uncovered, but some areas that you think are dense enough to possibly ignite or be ignited or already ignited once they're uncovered.
Okay. The first part of the question, are we looking at the way that our solar system formed? I don't know. I don't know the answer to that one. If I were to speculate, I might speculate and say no, that maybe we're going to rule off one of the mechanisms that would form our particular kind of solar system. I might refer you back to the stuff that we did in the spring about Herbig-Haro objects and disks that might be a better look at how
the newborn stars with the jets.
The newborn stars with the jets. The second part of your question, can I point at other regions in there where new stars are forming? In fact, I can. If you look at those elephant trunk structures, buried down inside each of those elephant trunk structures, there are new stars that are forming. You know, for example, the pictures on the screen now, if you look at the pillar on the left and up near the top of it, we're seeing eggs being uncovered today, and we're seeing the stars that are uncovered. But if you go and look at that in the infrared, you see that the whole inside of that is bright, and that buried inside of that are more stars that are forming. And so if we could come back in 10 or 20,000 years, the eggs that we see today might be gone. Their stars, or not quite stars, would be totally uncovered, but there'd be new eggs. The stars that are forming in there today that will be uncovered in 10 or 20,000 years.
Jeff, just to clarify something, I think that you're being a little too conservative, and that is, the evidence is pretty strong that our solar system did not form this way, because there are all kinds of sort of artifacts lying around that tell us that our planets were built up from a disk rather than burned down from radiation from the outside. So that although it may be possible that this process can make sub-solar scale things, it's almost certainly the case that the sub-solar scale things in our solar system were not made this way.
The question here is whether embedded down in the heart of any of these eggs there might be the beginnings of disks that might be nascent systems, and there are...
that's possible.
That's an area that there's lots of speculation and lots of ongoing work.
The two big stars that are eroding are things that are going to burn out pretty rapidly.
That's right.
And so you can later on have star birth occurring in this nebula that may make you a normal, if I may put it that way, star and solar system.
Right. The other thing that's interesting here, though, is that when those massive stars finally reach the end of their lives and explode, become supernovae, then that supernova is going to send out a shock wave. And what's that shock wave going to interact with? Well, it's going to run into exactly the things that we're seeing in these pictures. And so the thing that got me into this business a long time ago, in fact, was working on that end of the puzzle. And I'm excited in seeing these also because it lets me better understand what the cloud looks like when that shock wave hits it. So lots of connections here.
Just one last mechanical question. Talk about photoevaporation. Is the material in there actually boiling off, or what is happening with the UV light?
Okay. When you say evaporation, when you think about evaporation in your kitchen, you're thinking about water going to gas. Okay. There's a phase transition.
Or cookies disappearing.
Or cookies disappearing. That's right. That happens in my kitchen too. But you're talking about a phase transition. You're talking about a liquid becoming a gas, material going from one phase to another phase. When we talk about evaporation here, what we're talking about is a different kind of phase transition. We're talking about gas going from a phase that is dense and cool, so cool that the atoms stick together and form molecules, and having that go into a phase that instead is hot and is much more diffuse, and that not only have the molecules been broken up into their constituent atoms, but that in fact electrons have been peeled off of the atoms themselves to make ions. And so when we say evaporation in this case, we mean that kind of a transition between that cool, dense medium and that much hotter, more rarefied medium.
And to make it happen, you really need a fair region that is very thin. You couldn't do it if you hadn't broken out of your bubble, in a sense. broken out of your dark molecular cloud and had plenty of place for that material to
Yeah.
evaporate into.
Yeah, the exciting thing, for that part of the story, the exciting thing in Space Telescope is that even though this nebula, you look at the ground-based picture and it's this huge object, but what we find with Space Telescope is that the physics is happening. The processes that shape that nebula are happening not on the scale of this vast nebula, but instead are happening on the scale of this exquisitely thin edge between the molecular cloud and this hotter material. And it's a little bit like saying that you know, the human body is a large object, but if you want to understand it, then you need a microscope, because you need to understand about how cells work, and you need to understand about how blood cells flow through capillaries and all of that kind of stuff. That's really what the Hubble Space Telescope is doing for this kind of work. It's our microscope. It's the thing that we can use to look at these nebula, to look at regions of star formation, to look at supernova remnants, and see them at the level that lets us understand the processes at work, which are things that happen not over vast scales, but over very, very small scales.
I think one of the things that this image has shown that really was a victory was the actual filamentary trails leaving the dense material. So for the first time, you can actually see the stuff evaporating as lines of material.
I think our satellite time is evaporating, too.
We'd like to get around to some of our other NASA centers. Goddard, please give your name and affiliation. Go ahead.
This is Frank Roylance from the Baltimore Sun. This is for Bruce Margon. I wonder if you can give us some guidance here as to how definite you all are and how definite we ought to be about this interpretation of these images. And also if you can tell us to what degree this has all been theorized before, or whether this has all arisen out of this image.
It is certainly the case that people have previously discussed the idea that radiation from a previous generation of young stars might sculpt the local area. So the theory was around before, but I think it's really fair to say that no one has ever shown a picture where everyone points at the picture and says, that has to be erosion by radiation. There's no other way you can get such an incredibly sharp edge. So although there's never any certainty, the proof just gets better and better, in my mind, this observation takes us in one jump from no real observational evidence that this process works, even though people suspected it, to very strong observational evidence that this process actually happens. I hope that answers what you're driving at.
It also showed the direct involvement of the more massive stars, the very bright stars, in the cloud that is forming the less massive stars. The thing you're calling nurture versus nature. It's showing a real environment.
We can clearly see the stars that are responsible for the radiation bombardment, for example. So there's very little left to chance here. There's no, well, you know, if something were there and if it had this spacing, then maybe it would have this effect. We can see the cold gas. We can see the external exciting stars. We can see the effect.
And in fact, if I could, as we were talking earlier, you heard us speculating about what about brown dwarfs, what about planet formation, what about Jupiters. You heard us speculating about a lot of that stuff. We won't know the answers to all those questions until we go out and get real data. And at some point we'll get data that lets us look at it and say, yeah, that's what's going on. I guess that there's been a lot of speculation about the role that massive stars play in the formation of stars around them, triggering new star formation, shutting down ongoing star formation. But what's new here is a picture that you look at and you show it to anybody in the field, and inside of about 2 minutes explaining what they're seeing, they're going to say, yeah, that's what's going on there.
All right, we'd like to come back to NASA headquarters to see if there's any questions here before we finish up for the day. Dave?
David McAlery, VOA again. This almost borders on the philosophical, but is this nature's way of limiting star population because it doesn't like a density, a certain density?
In a sense, yes.
We know, of course, that very massive stars do manage to form themselves occasionally.
But we also know that there are very few highly massive stars and many, many more lower massive stars.
It really reminds me of, you know, you watch the nature programs on television, some of these species of birds where the largest nestling monopolizes the incoming worms from the mother bird, and pretty soon the siblings waste away. And
but regardless of this hot star turning on, you're still going to have very many more lower massive stars than the hot star. And in fact, Jeff says in this ground-based image that the hottest star provides 50% of the energy to blow away the regions that you saw. So that was one star having a real major impact. And the others, you're going to see lots of low-mass stars still. But as you say, not as many as you would have expected if you hadn't had the evaporation.
Yeah. The point is that as soon as you get stars that are 8 or 10 or 20 solar mass stars, that they totally change the character of what's happening around them, and that's what we're seeing. The joke that comes to mind is the old joke about where does an 800-pound gorilla sleep? Wherever he wants to. Well, you know, what does a 10 or 20 solar mass star do to its surroundings? Whatever it wants to. And we're looking at the fallout of that process here.
With that, I think we've come to the conclusion of our questions from headquarters as well as the center. So we'll bring our space astronomy update to a close today. Thank you, panelists, and thank you, everyone. We'll see you next time.
About a light year long, yeah.